All right, folks, we are back at section 12.21 talking about the probabilistic PCA model and doing maximum likelihood estimation of the parameters of that model. Now, you'll remember that in that model, we had that, the Z's were coming from, we had some latent variables, and they were coming from an isotropic Gaussian. And we said that X given Z is distributing according to W times Z plus mean, and then it has some additional variance on top of that. So the idea is now we want to estimate that given this model, we want to do some maximum, and we've got like lots of observations of X. We want to estimate these parameters W and mu and sigma squared. And so that's kind of what we're going to be doing today. So the very first thing we'll need to unpack a few things. So we'll remember that because of the way that the latents are Gaussian and the conditional distribution is Gaussian, so the marginal distribution on the observations is going to be Gaussian, and it's going to have these simple properties that its expectation. So if X is WZ plus mu, its expectation is going to be, well, the expectation of this goes to 0, so it's just going to be mu. And its covariance is just going to be the covariance contributed by the WZ term, which is WWT, plus this additional term from the sigma squared, which you guys can't quite see, so I'm just going to add it down there. Right. So this term actually is going to be this term over here. We're going to call C. So and we've already called it C before. So C is going to equal to WWT plus sigma squared I. Okay. So essentially we're just saying here. So now we're going to set up the likelihood of our parameters, and where our observations are independent. So we're just going to get the log. The log likelihood is going to be the sum of the contributions from each data point. And they're all dependent on W, mu, and sigma squared in this nice Gaussian way. And so that's where all of this stuff comes from, right? So this will be kind of like a 2 pi term that's always around. This is going to be this covariance term, this log determinant showing up. And then this is going to be the argument to the exponential. And our job is going to be to essentially maximize this with respect to the parameters and see what we get. Okay, so that's what we're going to talk about today. And the solutions are described here. I've actually got I made a blog post about it, just essentially doing the same thing, but it's all actually quite straightforward. We'll talk about how to achieve it, but it's very straightforward. So we talk about the maximum likelihood solution for the projection weights, how you go from the latents to the observations, and we'll do the maximum likelihood solution for the variance. And we'll talk about some of the nice properties, for example, where the rotational redundancy comes in, what the variances along each of the different directions are, which will have some cool properties. And yeah, then at the end, we're just going to talk about some of the interesting limits and, some of the computational aspects, like how this thing scales with dimension, which, yeah, we'll get to it. Okay, so let's do that. But it's, I think, ultimately quite a simple, in principle, quite a simple section, right? All we're doing is we've got this log likelihood, and we're gonna maximize it. And we're gonna maximize it using computing the gradient, setting it to 0, and from that, essentially everything follows. Okay, so let me erase all of this stuff. Okay, good. And I'm in the middle of the screen, which is great. All right, so let's start. So we next consider the determination of the model parameters using maximum likelihood. So given a data set of X of observed data points, probabilistic PCA can be expressed as a directed graph, which is shown up here. We won't talk about this just yet because we haven't covered graphical models yet, and it's not really necessary at this point. So as I just said, we've got this log likelihood become the sum of contributions from each of the terms. They're all being, that's kind of what this graph says actually, that all of these terms, you have these latents, you have these observations which we've made, and you have parameters that determine those observations, and there's n such observations. So it's kind of a compact way of essentially summarizing the same information. But you can just do it. You don't have to worry about that. You can just write out that, okay, these are Gaussians with a certain mean, a certain covariance, and this is exactly what you get. So this is what's so easy about this particular formulation. Everything's Gaussian. It just works out really nicely. Okay, so the first thing we want to do is figure out, what are our parameters? We've got the mean, the projection from z to x, and the variance. It's kind of isotropic variance. Okay, the first thing we're going to figure out is just the mean. So all we do is we set the derivative of this thing to, with respect to mu to 0, and it's easy enough to show. You can just see it's going to essentially have terms like this showing up, and it's going to be n of them. So you're going to get that n times mu is going to be the sum of those terms, and that's where the mean comes out. So that's kind of a very simple one to try out. You should just be able to do it. There's a c minus 1 in there. It's not going to matter. So just because c is going to be full rank, etc. So you can it'll just drop out basically. Okay, so now once we've got that mean, we plug it back in, and we get an expression that looks like this. So now it doesn't depend on the mean. It only depends on the covariance and also the data covariance in this particular form. So now we want to maximize this. And again, this is in principle straightforward. The only thing that I had to look up in tipping and bishop was, so the interesting thing that happens, you essentially get kind of a few cases. You get a case where W is 0, and then there's kind of I think it's like a full rank case, and there's going to be a case, but that's the interesting one, where W is not kind of fully, it's not square. And so that's the one you have to be kind of a little bit careful with. You can look up the paper, it's quite readable. I'll also make a post link to my blog where we talk about the derivation. It's very straightforward. But what you find is when you actually do that, is that your maximum likelihood weights have a form like this. So let's go through it. So first of all, these m's are going to be whose columns are given by any subset of the eigenvectors of the data covariance matrix. So this is kind of an interesting one, right? So you can take any m of any subset of those eigenvectors, you can use them. But it turns out, of course, that if you actually want to minimize, so any of those will be an extreme point. You know, whenever what's it called, a critical point. So you know, when you're like doing this procedure of setting gradients to 0, well, of course you don't always find those points aren't always going to be like the maxima, right? So many of them can be, they can be saddle points where, yes, indeed, the gradient is 0, but in some directions it's going up, in other directions it's going down. And it turns out that for any subset of, you can take any subset of m eigenvectors of your data covariance, and they will form, and their corresponding eigenvalues. And they will be a saddle point, except for the one where you take the top, m eigenvectors, and that will actually be a maximum. So that's kind of the one you're after, and it kind of makes intuitive sense based on our discussion before that you essentially want to kind of capture the top m eigenvectors. But in my blog post, I cover at least why that's actually the maximum. Right, so you've got those eigenvectors there. You've got the corresponding eigenvalues here. The minus sigma squared is basically happening, obviously due to the additive variance term, and it will end up, and we'll see at the end that what this will mean is that your projections into that principal eigenspace that's going to be determined by this weights, they're going to have your kind of observed variances, because so we're going to be adding a sigma squared later. That's going to cancel this out basically. That's what it comes down to. And we've got this additional rotational degree of freedom, which we can set to the identity or something else. But it's basically a degree of freedom that we have available. Okay, so what does he say? That all of the stationary points of the log likelihood function can be written in this particular form, where U of m is a d by m matrix whose columns are given by any subset. So let's just write that, any subset. Any subset of size m of the eigenvectors of the data covariance matrix S. The m by m diagonal matrix Lm has the elements given by the corresponding eigenvalues, and R is an arbitrary orthogonal matrix. Okay, so corresponding eigenvalues, and R is orthogonal matrix. I think he means orthonormal. So R transpose the identity. Okay, so furthermore, they show that the maximum likelihood function is obtained when the m eigenvectors are chosen to be those whose eigenvalues are the m largest. So a similar result was conjectured, but no proof was given. Okay. All right, so I think that's kind of the first result is that the weight vector that this projection weight. So you're going to take on those latents, and those latents are essentially going to give you. Remember how they mapped into the observation space, right? We said x was w times z plus the mean, right? And so we can just write this as sum wi zi plus the mean. So essentially those latents are telling you how much kind of the strength that you're going to be applying in at least if R was the identity, along those directions. And if R isn't the identity, well, some rotation you can the rotated version of those latents tell you how much you should move along the directions of the data that are in the data, the eigenvectors of the data. And they're going to be amplified by some amount that's going to be related to those, the eigenvalues. So the stronger directions are going to be driven more, and then there's a rotational degree of freedom. Okay, so it's kind of natural that these aspects are coming out. And we'll also see this in the derivation that, okay, so it turns out, so now you've got the weights, you've got the mean, the final thing you have left is the additional the variance that you should add. And it turns out the variance that you end up adding is going to be the average variance in the directions that you didn't take. Right? So it's like you have some of the directions. So you're going to be adding sigma, this sigma squared to everything. And that amount is going to be, the maximum likelihood amount. So, and you've used the weight vector to pick, the top m eigenvectors, or whichever ones you've chosen. But the best ones to pick, the ones that maximize the likelihood, are the top eigenvectors. And the variance. So, what are these? Well, these are going to be the variances along all the other directions. So and there's d minus m of them because you've picked the top m, and now there's d minus m. So now you're essentially taking the average variance in the other direction. So sigma squared ml is the average variance associated with the discarded dimension. So that's exactly what we're seeing here. And we'll see that in the derivation. Okay, now because R is orthogonal, it can be interpreted as a rotation matrix in the m by m latent space. If we substitute the solution for W into the expression for C and make use of the orthogonality property, we see that C is independent of R, right? So this is all this is saying is if you've got C is W transpose plus blah blah blah. Well, if you've got something times R and then R transpose something else, well, this is just going to become the identity. So it is going to equal to the something times the something, well, transpose, I suppose. So the R doesn't matter basically. And that's just kind of saying, well, there's some arbitrariness in how you determine you call your latents, right? They're kind of rotationally symmetric, so you can just kind of move them around. It doesn't really matter. For the particular case of R equals I, we see that the columns of W are the principal component eigenvectors scaled by the variance parameters lambda I minus sigma squared. So that's all we're saying, that this is the identity. The columns of W are the principal, yeah, exactly, right? So WML is just going to have each of the columns is going to be eigenvector, and it's going to be being scaled by and the eigenvalue minus sigma squared to the square root. So that's just this part. That's all that's saying. Now, the interpretation of these scaling factors is clear once we recognize that for a convolution of independent Gaussian distributions, in this case the latent space distribution in the noise model, the variances are additive. Thus, the variance lambda I in the direction of an eigenvector ui is composed of the sum of the distribution lambda I sigma squared from the projection of the unit variance latent space distribution plus an isotropic contribution of variance sigma squared, which is added in all directions by the noise model. Okay, so what does that mean? We're going to see that now. Like, what does that imply? Okay, so let's have a look. So it's worth taking a moment to study the form of the covariance matrix given by 12.36. And if you guys can see, I'm going to write that out here. That's just C is WWT plus sigma squared. Consider the variance of the predicted distribution along some direction specified by the unit vector v, and it's just a unit vector, right? Which is given by, and let me erase all of this stuff. Okay. Given by, so this was, this is how you compute variance along arbitrary directions. You just project them onto a covariance matrix. First, suppose that V is orthogonal to the principal subspace. In other words, it is given by some linear combination of the discarded eigenvectors. Okay, then V transpose U is 0. So where is this U coming from, right? Well, U is coming from, so if we actually expand this out, this is going to be U times UM. I'm just going to write that minus sigma squared times U transpose plus sigma squared, right? That's what we have. So all he's saying is, well, if you project V onto U, well, this whole left component is going to just drop out because it's going to come out to 0. And hence, V transpose CV is sigma squared. So if you're talking about projections along the directions that you're not using, you get a sigma squared variance in them. So the model predicts a noise variance orthogonal to the principal subspace, which from 12.46 is just the average of the discarded eigenvalues. Now suppose V is UI, where UI is one of the retained eigenvectors. Remember, all of the eigenvectors all together are forming a basis, and we've chosen some set of them. They're forming an orthonormal basis. Where U is one of the retained eigenvectors defining the principal subspace. Then V transpose CV is, well, this part goes through, right? You get the corresponding eigenvalue dropping out. So it's eigenvalue minus sigma squared, and you're adding a sigma squared, so you get lambda I. So they kind of cancel out, the sigma squareds cancel out, and you get the observed variance in that direction. So this model correctly captures the variance of the data along the principal axes and approximates the variance in all remaining directions with a single average value sigma squared. So that's pretty cool. So let's just do that. Yeah, so kind of a really very neat property. Okay, one way to construct the maximum likelihood density model would simply be to find the eigenvectors and eigenvalues of the data covariance matrix and to evaluate W and sigma squared using the results above. And we could set R to be I for convenience. However, if the maximum likelihood solution is found by numerical optimization or through EM, then resulting value R is essentially arbitrary. This implies the columns of W need not be orthogonal, right? So essentially it's saying that if you use some other method, you're not explicitly, you're just solving for W. So you're not explicitly setting R. And so it might end up that R isn't the identity. And if that's the case, then the columns are not going to be orthogonal. So what does he mean by that? Well, let's consider, okay, so remember what W was. So W was U, I'm just going to put something here, this bit doesn't matter, R transpose. Now if we had, let's say R transpose was the identity. So if we set this to the identity, now then if we look at the columns projected onto each other, then W transpose W is going to be what? It's going to be L is the diagonal, U transpose U, L, and so it's going to be L squared. And so this is a diagonal matrix, so the columns are going to be perpendicular to each other. So that's the case when R is the identity. But if it's not the identity, well then obviously you can see that what you'll get is R, L squared, R transpose, right? And so now this is going to be some matrix. But it's not going to be a diagonal matrix in general. So that means the columns are actually, they're not going to be orthogonal. So that's all he's talking about. If an orthogonal basis is required, you can post-process it. So you can actually figure out what R is, remove it if you wanted to, or you could do EM. We haven't talked about that, but you can do it in such a way to do orthonormal principal directions. Okay. Rotational invariance in latent space represents a form of statistical non-identifiability, right? So it says that, look, we can only identify W up to rotation. Analogous to that encountered for mixture models in the case of discrete latent variables. Here, there's a continuum of parameters, etc. Okay. If you consider the case of m equals d, so now we're not actually, so we're taking all of the eigenvalues. We're just finding the axes of the full space that determine our data. But there's no reduction in dimensionality. Then u of m is just u, L of m is L, so there's no sigma squareds. Making use of the orthogonality properties, we see that the covariance of the marginal distribution for x becomes blah blah blah, which is going to be equal S. And so we obtain the standard maximum likelihood. Oh yeah, and here they wouldn't be in sigma squared anyway, because this is just like, all he's saying here is that you just take all of the eigenvalues, not just like a subset of m, you're taking all of them. So in that sense, then the covariance in that setting just becomes the full covariance of your data. So we obtain a standard maximum likelihood solution for an unconstrained Gaussian distribution in which the covariance matrix is given by the sample covariance. Yeah, I think essentially what he's just saying here is that in that setting, you're trying to find the covariance, mean and covariance of a Gaussian distribution, so there's no dimension reduction anymore, and indeed, we already uncovered the mean, and here we uncover the covariance. Okay, conventionally, PCA is generally formulated as a projection of points from the d-dimensional data space onto an n-dimensional linear subspace, right? We're always thinking about projecting down, but in probabilistic PCA, and also kind of many of these generative like perspectives on these, is most naturally expressed as a mapping from the latent space into the data space via 12.33. So that was the Wx plus Wz plus mu, etc. For applications such as visualization and data compression, we can reverse this mapping using Bayes' theorem. So again, we want to go from the data to the latents. How do we do that? Any point in data space can then be summarized by its posterior mean and covariance in latent space, and we already have expressions for these. And so the mean, for example, looks like the projection of the mean subtracted data point onto the weight matrix, the projection matrix, and then kind of dividing out by this m minus 1 is, so it's kind of a regularized version of W, being regularized by the additive covariance. This projects to a point in data space given by that. Note that this takes the same form as the equations for regularized linear regression as a consequence of maximizing the likelihood function for a linear Gaussian model. So I think what he's talking about here is that you can just view this, everything we're doing here as just like what we were doing in the linear regression case when we were looking at, we had some, we're trying to infer the weights, right, that would take us, given some set of observations, get some set of inputs, some set of outputs. We're looking at, what is the predicted distribution, all that stuff. It was kind of a very similar setup. Again, just linear Gaussian models in another perspective and in another application. So that's why kind of these look the same. So I think we had an equation there where we had the expectation of, yeah, I think it was like the predictive distribution or something like that. We'll have to go back to have a look at it. And it looked exactly like this. So there was like, I think we had a phi in that case. So it's kind of our feature vector. And then we had like our weight covariance, but it was essentially the same form. So that's what he's talking about here. Have a look at 3.3.1 if you want to know what that's all about. Assume the posterior covariance is given by n is independent of x. Okay, so now one final point. So if we take the limit as sigma squared goes to 0, then the posterior mean reduces, so this term drops out, and you actually just end up getting a projection, the least squares projection, orthogonal projection of the mean subtracted data point onto the principal subspace. So remember, this was one of our versions of PCA, right? Like finding a principal subspace onto which we could project the data with the least reconstruction error. Well, that's essentially this. Essentially, this is exactly what we're doing here. So in the limit as sigma squared goes to 0, we just get the our projection of the data points agrees with the projection from PCA. But if sigma squared and the posterior covariance in this limit is 0, however, and the density becomes singular. So that's kind of one of those weirdnesses, right, that we're kind of trying to overcome. that perhaps one shouldn't be so certain that actually these are the projections. We want to get kind of sensible. We want to get sensible covariances, and with probabilistic PCA, we would. Whereas here, it just becomes like a single. It says this point, this observation for sure is going to map onto a particular point in that principal subspace, and there is no onto the exactly, yeah. So I was just a little bit confused because because the projections onto that principal subspace are going to be the latents. Just want to make sure I was saying that correctly. So an orthogonal projection of the data point onto the latent space, which is the principal subspace. And indeed, so and it's just going to say that, like, in the PCA model, you're effectively saying that you're absolutely sure exactly where that latent is, whereas in probabilistic PCA, we're going to have some covariance on that, so some sensible uncertainty. For sigma squared greater than 0, the latent projection is shifted towards the origin relative to the orthogonal projection. So you can kind of work that out, but that essentially comes from this regularization aspect, where essentially you scale by sigma squared towards 0. So you're kind of shrinking the estimates. And there's an exercise on this that's might be worth doing. Okay. Now, finally, we note that an important role for the probabilistic PCA model is in defining a multivariate Gaussian distribution in which the number of degrees of freedom, in other words, the number of independent parameters, can be controlled while still allowing the model to capture the dominant correlations in the data. Right. So here we've chosen how many what dimension of latents we want, what the dimensionality of that latent subspace is, so we can pick like how many of the top correlations we want to keep. We call that a general Gaussian distribution as d plus 1 over 2 independent parameters in its covariance matrix. So that's just just the diagonal and everything above it, for example, plus another d parameters in its mean. Because the number of parameters scales quadratically with d and can become excessive in spaces of high dimensionality. If we restrict the covariance matrix to be diagonal, then of course we only have d independent parameters. So now it only grows linearly. We want kind of linear growth, but of course now treats the variables as if they're independent. This is Gaussian, so if they're uncorrelated, it means they're independent, and hence can no longer express any correlations between them. The probabilistic PCA provides an elegant compromise in which the m most significant correlations can be captured while still ensuring the total number of parameters grows only linearly with d. So basically all we're going to find out down here is that the number of parameters, if you count them all up, is actually going to be linear in this d parameter, and you can keep your m if you're keeping your m fixed. So if you say you want like the top 2 correlations, well, you can always get that even if you have 10,000 dimensions. You're kind of a little bit freed from that. I think it's, I don't know. I think that's, yeah. I mean, it's technically correct, but I guess my thought would be that as your dimensionality goes up, there it can be. It's not so much m is fixed and d increases. Sometimes what actually matters is the ratio of these, and this ratio will stay constant. So yes, you have 1,000 dimensions, but so m is going to be called some alpha times d. So this thing ends up being still quadratic in d, but maybe with a small alpha in front. So I think it just really depends. Like it depends on what we mean and how our correlations grow with dimensionality. But anyway, let's kind of follow what he says. So we can see this by evaluating the number of degrees of freedom in the PPCA models as follows. The covariance matrix C depends on the parameter W, which has size d by m, right? So d dimensions, m directions, and sigma squared giving total parameter count of dm plus 1. However, we have seen there's some redundancy in this parameterization from this orthogonal matrix. So that's going to and this R itself has total of m minus 1 over 2 independent parameters. So it's kind of think of it as a rotation matrix. It's a special. You can think of it similarly to an essentially you can think of it as like a, well, it's not like a covariance matrix. Basically, in terms of counting the number of parameters, yeah. So let's just go through it. So in the first column of this matrix, there are m minus 1 independent parameters because the column vectors are normalized. In the second column, there are m minus 2 parameters because must be normalized and orthogonal to the previous one, and so on. So if you just kind of continue this, you get a total of this many parameters. And so the number of degrees of freedom we have to kind of specify, in C is, well, this is coming from W minus the ones we lose in this rotational, because they all give the same. So you don't that rotational freedom that you would have that's coming from here, you actually don't have because it gives the same C. So the number of independent parameters in this model is therefore grows only linearly with D for fixed M. If we take M equals D minus 1, then we recover the standard result. In this case, the variance along D minus 1 linearly independent direction is controlled by the columns of W. The variance along the remaining direction is given by sigma squared. And if M is equal to 0, so we don't take anything, then we just kind of get the isotropic covariance. So we just put all of our variance into sigma squared. Well, yeah, so I don't know. I mean, I think it's, I guess technically it's linear in the dimensionality, but I think M can also grow with D. So to the extent that that's a real gain, I'm not so sure. I guess it depends on your particular application. But anyway, so I think that was this section. I think it was all pretty straightforward. At least the derivations you'll see, you'll see in my notes, it's just computing gradients, setting them to 0, and then just being careful about the different cases that are involved. That was a tip from the paper. The paper itself is also quite readable. I haven't read the whole thing, but I've kind of gone through the mathematical appendices to some extent, and it seems quite manageable. So yeah, so essentially we find the principal with the subspace. We just offset the eigenvectors by some amount, which then we add on so that we capture all the variance in the principal directions, and then the variance along the maximum likelihood variance that we add is going to be the average variance along the direction that we don't, the ones that we discard. So kind of quite intuitive results. And we've got this additional degree of freedom. Okay, cool. So I think that's all I wanted to say about this section. And next time we'll come back and we'll talk about doing EM. So kind of estimating these parameters, but kind of from a different perspective from the EM algorithm. And I think since we haven't covered that, I might just have a separate section in between where I give a little crash course on EM, just so we're all up to speed on what we need to understand the section. So I hope I'll see you then when we cover EM and then EM for PCA. Bye.